All right, in this lesson, we're going to classify types of discontinuities. So we're going to begin by looking at three discontinuous graphs. None of these graphs right here can be drawn without lifting our pencil, therefore none of these graphs are continuous. And I think that's kind of an intuitive thing. All right, so what we're going to do first of all is we're going to kind of study the different types of discontinuity. We have a whole, which is considered a removable discontinuity. So one, we're going to classify each of the discontinuities occurring on these three graphs as either a whole, number two, a jump discontinuity, or number three, an infinite discontinuity. So just kind of let your intuition kick in. All right, so let's look at graph one. We're going to work our way from left to right and then pause when we get to an interesting, juicy little place on this graph. So when we jump on graph one, right over here, far left, and we continue along, we have this sharp turn. That's okay. Come down here. Notice that you have an open circle, but on the other side of this same open circle, the graph starts again and it continues down this way. So let's just kind of focus our attention right here on this graph at x equals 0. So coming over here, if you had to choose and you're just guessing, and there's no wrong answers when you're guessing, would you classify that discontinuity right here at x equals 0, where you have to lift your pencil? Would you classify that discontinuity as a whole, a jump, or an infinite discontinuity? Well, if you said whole, then you're correct. Okay, this is called a removable discontinuity. I don't like to use the word whole because sometimes students think that every time they see an open circle, here, 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 and here, that they think that they have a whole. So I like to say that this is a removable discontinuity, and the only type of removable discontinuity is a whole, so we're really saying the same thing. Okay, so this is actually a removable discontinuity, and again, if you want to call it a whole, that's fine, just be careful. So this is a removable discontinuity, which just means that if I were to take one point that's lined up vertically at x equals 0, let's say that this graph also had this point right here at x equals 0. We had an open circle here, okay, but we had this filled in circle here. This is a removable discontinuity or a whole because if I took that one random point and I slid it down and I filled in this open circle, then the graph would be made continuous. So if you can take one point, okay, and move it, now maybe the point was down here. I couldn't have a point above and below because then I wouldn't have a function. But let's just say that that random point had been sucked out of here and moved down vertically to here. This is still a removable discontinuity or a whole. Okay, what if we didn't have either, like in the original problem? We didn't have either one of these points. It's still a removable discontinuity. All right, let's go back to the graph and continue moving along. So I'm moving along the graph and I stop here at this closed circle. But then I'm going to have to move up here for my graph to begin again. And sorry about my Sharpie, it kind of made this look like a closed circle, but it's really open. So imagine this to be an open circle. I couldn't have a closed circle here and a closed circle here because then I wouldn't have a function. All right, so at x equals 2, what type of discontinuity do we have? Do we have a removable or a whole? Or do we have a jump discontinuity or an infinite discontinuity? And hopefully your intuition is kicking in and you said jump discontinuity. And that's correct because you actually have to jump from this y value of -1 to all the way up here to this y value of 2. So that's called a jump discontinuity, also known as a non-removable, but I usually just say jump discontinuity. All right, so at x equals 2, we have a jump discontinuity, and then from there we would just continue downward. So notice that I have an open circle here. So just because I have an open circle here doesn't mean that I have a whole or a removable discontinuity. And like I said, some students thought that anytime they saw an open circle, that automatically made that discontinuity a whole. But that's not what a whole is. A whole is where the graph comes together except for at that one particular point, like right here. All right, so go ahead and maybe pause the video and look at graph 2 and 3 and see if you can classify each of the points of discontinuity. All right, graph 2. Let's jump on the graph. I continue downward, 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 downward. So I'm getting infinitely small. Well, There is a break in the graph here. I'm going to have to lift my pencil to jump over here on the other side of this vertical asymptote to continue drawing the graph. So at x equals -1, x equals -2. At x equals -2, is that a removable discontinuity, a hole? Is it a jump, or is it an infinite discontinuity? So if you thought infinite, then you're correct. So the graph is getting infinitely smaller and smaller and smaller and smaller. So we classify this as an infinite discontinuity, and that suggests a vertical asymptote, which is what I can see visually. All right, let's jump back on the graph. Here we go. We're coming around this way. At x equals 1, now I have another place where I have to lift my pencil before I can continue to draw the graph. Okay, well, what kind of discontinuity is occurring at x equals 1? Well, that looks like it's a removable discontinuity, or a hole. And then the graph continues onward from there. So graph 2 has two discontinuities, one infinite and one removable, or a hole, if you want to call it that. All right, look at graph 3. There's a lot of breaks in this graph. There's 3 places where I'm going to have to lift my pencil. So let's categorize these discontinuities. Jump on the graph. So this graph is getting infinitely large, larger, large, and then on the other side, it's infinitely small here. So we still have a break in our graph, and we call that an infinite discontinuity because it's a visual of a vertical asymptote. Jump back on the graph. Okay, notice that both of these right here are open circles. One of them could have been closed, but not both of them because I wouldn't have had a function. Okay, and it's okay if both of them are open as well. Okay, so what type of discontinuity is occurring here? Well, this is going to be a jump discontinuity because you got to jump back up here to this other open circle before you can continue on the graph. So at x equals 1, I have a jump discontinuity. And then the final discontinuity is occurring at x equals 5 up here, and that's going to be your removable discontinuity, or your hole. So I guess the big takeaway is open circles don't indicate that you have holes all the time. Okay, it could be that the open circles, look real carefully at the structure of the graph, the open circles could, indicate that you also have a jump discontinuity. So just be kind of careful with that. Okay, so coming back here, looking at the top of these notes, if you've taken pre-AP pre-cal, then you probably have already seen these notes, but I wanted to give you kind of a quick reminder about discontinuities. They're important to calculus as far as the concept of limits. So right up here, we've got a statement. It says a discontinuity is removable if the hole can just be colored in to fix the situation and make the graph continuous. So on graph 1, if I were to fill in this open circle, the graph would be made continuous. Now, keep in mind what I said earlier. You may have on the original graph had a point here. Okay, for me to color this in, I wouldn't have to actually color it in. I would have to first look to see if there's a random point that I could move. If there's not one, then I think, well, since there's not a point, vertically above or below this open circle, then I would just fill this in. So this right here, even if a point's here, is still a removable discontinuity, a hole. All right, there are 2 kinds of non-removable discontinuities, jump and infinite, and I think we saw that through our work. All right, so and here's a categorization right here specifically. So for graph 1, there's a removable discontinuity at x equals 0. Yes, there is, regardless of whether there's a point there or not. That would not be considered a jump discontinuity, even if a point was here. I think that's another kind of gray area for students. There's a non-removable or jump discontinuity at x equals 2. Graph 2, a non-removable or infinite discontinuity at x equals -2. When you go to categorize them, it's okay if you just say infinite. You don't have to say non-removable. There's a removable discontinuity at x equals 1. Again, had there been a point here, or maybe that point had been down here, okay, then that's still a removable discontinuity, not a jump discontinuity. So the jump discontinuity is really where there's, 2 breaks in the graph here. You have to start, continue on the graph at a different y value than what you see here. Like these 2 y values near this open circle are coming into 1. So maybe you can kind of think of it that way. All right, and then the last one, the summarization is there's an infinite discontinuity at x equals -2, there's a jump discontinuity at x equals 1, and there's a removable discontinuity or a hole at x equals 5. So hope that reminded you or helped you understand the differences between the types of discontinuity that we're going to study. There are other discontinuities. There's an oscillating discontinuity, but for our course of study, we don't have to dig in and really learn that much.